the main theme of chapter 4 are finding extreme values of functions. In this diagram here is giving you the definition of what an absolute maximum or minimum is versus a local maximum or minimum. First thing I want to point out is that there's a difference between the location of where a minimum would be and then the actual minimum value itself. The location of the minimums or the maximums would be the x values along the x-axis. The minimum and maximum values themselves are the y values that are actually along the curve. So starting over here on the left, we have an absolute minimum right here at f of a. That's your maximum, or sorry, your absolute minimum. What makes it absolute is that it's the smallest of all the y values over the whole interval from a to b. Then we come over to where x is equal to c, and then we have this value up here called f of c. That value is a local maximum. It's only considered local because it's not the highest, it's not the greatest of all the y values because you have a greater one over here. But if you were to just look at a smaller neighborhood or interval of x values, like if I were to just look between where x is a and x is e, so just from here to here and sort of block out all the other parts of the function, well then that is a maximum over that interval. So it's the greatest values of the function nearby. And then similarly I have a local minimum right here at f, or at x equals e, and the minimum is equal to f of e. And again, it's not the lowest value on the whole interval from a to b, but if you just look at a neighborhood, a smaller interval of x values, so if I just look between where x is c and x is d, then it's the lowest one over that nearby interval, that neighborhood of x values that are close to where x is equal to e. And then of course up here at f of d, that would be considered the absolute maximum because it's the greatest y value on the whole entire interval from a to b. It's the highest of all the y values, so it's a maximum because it's the greatest, and it's absolute because it's the greatest. There is no greater value of f anywhere, so it's the absolute max. And then at f of b, we have again another local minimum. It's not the absolute min, that was way over here where x was a. But if you were just looking on a smaller neighborhood of x values, like if I were to block this off and just look at the x values between e to b, then this would be a local minimum. Actually, I need to go a little closer. I need to go from like here to here. If I were to just look from here to here, then this would be considered my local minimum over that interval. So what I want us to consider is where these maximum and minimum values occur, because that will help us learn how to find them. So we're going to notice that the maximum and minimum values occurred in one of three places. So we're going to have to always check for those three places. First category where they occurred were at the endpoints. When x was a, we had an absolute minimum value, and when x was b, we had a local minimum value. So if there's a max or a min, it will occur at either the endpoints, or it will occur when the derivative is equal to 0. So right here when x was c, if you look at the tangent line, the line that's tangent to the curve at x equals c, and then of course we know the derivative is equal to the slope of that tangent line. Here I have where the slope is 0, and then also right here at this local minimum value, notice how the slope of the tangent line there is 0. So the other place where you could have a max or a min is where the derivative is equal to 0. And again, that was right here and there. The third type of place where we had a maximum or a minimum value was where the derivative does not exist or is undefined. And that actually occurred right here. We have sort of a corner right here where x is d, where it's the function was increasing and then it just sort of abruptly stopped and started decreasing. It wasn't smooth like here where the derivative was 0, but it did change direction, which created a maximum value because the function was going up, stopped, and then started going down. Where it stopped was our maximum. So sometimes that could happen when the derivative does not exist. So those are the 3 places where we're going to check. Also, I wanted to tell you that these categories are referred to as critical points. Okay, then you may ask why. Why is it that the maximum and minimum values occur at these points? Well, the answer to that question is because these are the places on the graph where the function is either starting or stopping, and those would be at the endpoints. So like right here where x is a, the function's starting. And when it starts, it begins to increase. It begins to go up. So because it's going up after where it starts, the point where it starts is a minimum because everything else is now greater. And then likewise over here where it stopped, it was up here at this high value and then it began to decrease or get smaller and then just sort of stopped decreasing. That would be a local minimum because it's not going any lower than that. So where the function starts or stops, you're going to have either a max or a min depending on if it goes up or down before or after. So that's why the endpoints create maximum and minimum values. But it's also where the function changes direction. And so that happens at these critical points where the derivative is either 0 or undefined. Because you can see that in order for the derivative to be 0, the function has to reach a point where it's changing direction. So in this scenario, the function was increasing, it was going up, and then it stopped and then began to go down. Right there where it changed from increasing to decreasing, we have a slope that's 0, where the derivative is 0. Same here, the function was going down, it was decreasing, it stops, and then it begins to increase. So right there where it went from decreasing to increasing is where I have a slope of 0. But these were nice and smooth changes in direction. Here the function is increasing and then abruptly changes direction and begins to decrease. But it changed direction nevertheless. So even though the derivative doesn't exist there, the direction of the function changed and created a maximum because it was going up, stopped, began to go down. So it created a maximum value right there. So the maximum and minimum values are going to happen either where the function starts or stops, so that's the endpoints, or where the function changes direction, which is when the derivative is 0 or is undefined. Now there's 2 theorems that sort of go along with this. And I'd like you to write them down here because these are important. We need to have all the details in order to do this, in order to do these problems effectively. The first theorem is that if f is continuous, meaning it's connected, all the values are connected on a closed interval, meaning that means I'm including my endpoints. So closed interval from a to b, which is similar to what I have up here, because these endpoints are included in the function itself. So if f is continuous, meaning connected on a closed interval from a to b, then you're guaranteed to have both. F has both a maximum and a minimum value on that interval. Now, if the function is not on a closed interval, then you're not guaranteed either one of these. Sometimes a function has neither because it's not on a closed interval. But if it is on a closed interval, then you're guaranteed to have both. It will have one of each at least, if not more. Okay, then the second theorem, and I'm not going to really word it the way the book does, I'm going to sort of abbreviate it my way, is basically saying that if a max or a min exists at some x value, we'll just call it c. So if it exists, so that's the condition of this theorem, if it exists at x equals c, and if the derivative exists at f equals c, or at x equals c, so if f prime of c exists, that implies that f prime of c is equal to 0. So what that means is, if a max or min exists at x equals c, then you're guaranteed that f prime of c equals 0. Okay? Now, the reverse of this is not always true. So just because a derivative is equal to 0 does not imply that a max or a min exists. And I'll just give you one example, and maybe we'll flip this over to the back. And that example, and this is just one of many, but is the example of the function f of x equals x to the third, because if you remember what the graph of x to the third looks like, it goes like this. And so at x equals 0, which is right here, you have a tangent line that is horizontal. The line tangent to the graph at x equals 0 is horizontal. In other words, f prime of 0 is 0. The slope of the tangent line, which is the derivative, at 0, f prime of 0, is equal to 0. But notice that that is not a max or a minimum value on the function. The reason is because the function never changed direction. The function was increasing that entire time. In order to have a max or a min, it has to change direction. It has to stop increasing and begin to decrease, and vice versa. But this function is increasing the entire time. And that happens every now and then. So just because the derivative is 0 doesn't mean you have a max or a min. So just something to keep in mind. But if you have a max or min, like if a max or min exists and the derivative exists, then that derivative must be 0, which is going to help us find these critical points. So these next 2 pages are just examples to help you be able to complete the bookwork in class. And I have each section sort of labeled with which problems in the book that they will help you with. So hopefully this can guide you when you're working in class and trying to figure out how to do certain problems. So with these first 2 examples, you're given a graph. You're not really given any x values or anything, because I just want you to see visually where the absolute max and absolute min occur. So in number 1, and remember, we're only looking at absolute extremes. We're not looking at local extremes. So I'm looking for only the highest or the lowest. And so I can see for number 1, the highest value would occur right here where x is c. And notice they just want you to identify the x value where the absolute extremes occur. So I can see that I have an absolute max at x equals c because there is no higher y value on this curve other than f of c. Likewise, I have a local minimum right here at b because there is no y value lower than f of b. So I have an absolute min at x equals b. So I'd like you guys to go ahead and try this one. Pause the video here and come back when you're ready to check your answers. Well, I'm hoping you discovered that there are no extreme values for this u-try. There would have been one right here where x equals a, but the problem is f of a does not exist. And so f of a would have actually been the maximum value, and it doesn't exist, so there is no maximum value there. And you might be thinking, well, what about just here to the right of a? Well, it's one of those things where the function is getting up to but not including f of a. So there's like an infinite amount of numbers in there, and there's really no maximum because there's always one that's going to be higher than the last. So there is no absolute max. There would have been an absolute min right here at b, but it turns out that f of b is actually not the lowest value. It is actually greater than some of the values along this interval. Like if you look basically at all of these y values here and here, this is actually greater. So because this function was not continuous, you're not guaranteed any absolute max or min, so this was none. All right, then for example 2. This is where we're going to get to how you find the extreme values. So I will say this, before doing anything, if you can, it's always encourage to sketch the graph. It will just help you understand visually what's going on. So I want to sketch the graph of e to the negative x. And so I'm going to do that using stages. You may remember from calculus. The graph of e to the x has a horizontal asymptote at y equals 0. And it crosses through the point 0, 1. And then it shoots up exponentially fast. As x approaches infinity, this approaches infinity really, really fast. But you'll notice here that I have a negative being multiplied to the argument, or what you would consider inside the function, which is going to create a y-axis reflection. And so I'm just going to take this and swing it over the y-axis, but that doesn't change where my horizontal asymptote is, and that doesn't change this point 0, 1. Okay, so, oh, and another thing is I was given an endpoint. I'm given this from -1 to 1. So I'm looking from here to there. And it's a closed interval because I'm including the endpoint. So I'm looking from there to there. So you can tell just by looking at the graph that there aren't any interior max or mins. The max is at the left endpoint, -1, and the min is at the right endpoint, 1. And now what we're going to do is confirm algebraically, because this is what you'll have to do on the AP test. Well, we remembered from the first page that if there's a max or a min, it's going to occur either at the endpoints, which we can see that it does here, or where the derivative is either equal to 0 or is undefined. So what I'd like you to do for the first step is I'd like you to find the derivative. So I'm going to use chain rule here, and I have an e to the blob. So the derivative of that would be e to the blob times the derivative of the blob, which is -1. So it's negative e to the negative x. In step 2, I'd like you to find where that derivative is either equal to 0 or is undefined. So I'm going to basically take my derivative and then set it equal to 0. And then if you recall, a base risen to a negative exponent, you basically take the reciprocal of that. So what I want you to notice here is that this is never going to happen. Like 1 over something, especially e to the x, is never going to equal 0, because the only way a fraction could equal 0 is if the numerator is 0. Another way to see this is if you looked at the graph of negative e to the negative x, which means you would take this graph here, which was e to the negative x, and it has a negative in front, so you'd flip it over the x-axis. So I have the horizontal asymptote at y equals 0, and then you would just flip that down, so it would kind of go like this. And you'd have this point here at 0, -1. And you can see that the function is going to approach 0 as x approaches infinity, which even looking at the equation makes sense because you'd have 1 over infinity, so it's going to approach 0, but it's never going to actually equal 0. So there are no values of x that make the derivative equal 0, so now we want to see if there's any values of x that make the derivative undefined, and there aren't, because this derivative is smooth and continuous for all real numbers, so there are no values that make the derivative undefined. Okay, so step 3 is you check, or you plug in any critical points you may have found, which we didn't find any in this example, and then also your endpoints into the original function to see which one yields the highest or lowest value. Okay, so I'm running out of room, so I'm going to just block this off right here. So again, I had no critical points in this particular example. There were none. But I do have endpoints that were given to me in the beginning of the problem, which are -1 and 1. So I'm going to plug in -1 into the function, and I get e to the -1, which is e to the first power, which is approximately, if I look on my calculator, so I get e to the first power is approximately 2.72. And then when I plug in the other endpoint, I get e to the negative 1, which is approximately 0.37. 0.37. So I can tell from looking here that I have an absolute, and I know this is absolute because this has endpoints. So it's like it basically started here and then just kept decreasing that entire time. So I have an absolute max at 2.72 and then an absolute min, or sorry, at x equals negative 1 and it equals 2.72, and then an absolute min at x equals 1 and it equals 0.37. So let's write the answers up here. So absolute max at x equals negative 1 and it equals 2.72, and then an absolute min at x equals 1 and it equals 0.37. So remember, where the max is the x value, what the max is the y value. And so this would be our answer for example 2. But the steps, I recommend sketching the graph first so you can just visually see what's happening. Then to confirm analytically, because it says use analytic methods, step 1, you find the derivative. Step 2, you set the derivative equal to 0 and solve for x. And you also check if the derivative has any x values where it's undefined. These are called critical points. So step 2, what you're really doing is you're finding the critical points. And then step 3 is you plug in any critical points you may have found in step 2, as well as any endpoints if they exist, into the original function, because I want to see the extreme values of the original function. I want to see when these y values are at their highest or their lowest. So you plug it into that and you see which one's higher or lower. So now I'd like you to try with this example here. So the answer you should have gotten is that there's a local max when x is equal to the negative square root of 2/3 and the max is equal to 5.09. There's a local min when x is equal to positive square root of 2/3 and it's equal to 2.91. And the steps we use to check that are we find the derivative in part 1, which is 3x squared minus 2. Find where the derivative is either equal to 0 or undefined, and that happened when x was positive and negative square root of 2/3. Then in step 3, you plug in any endpoints if they exist, but there are none in this particular example. So we just check our critical points, and we have 2.91 for the square root of 2/3 and 5.09 for the negative square root of 2/3. And because there are no endpoints on this one, there's no way for us to really tell at this point if it's absolute max or min or local max or min. So we'll just call these both local, because even if you call something a local max or min, that could still apply to the absolute max or mins. But this way we're just kind of covering our bases, so we call them local. Okay, moving on to the next couple examples. So this is just another example to go with these problems here. It's the same steps, but I wanted to walk through them with you because this one's a little unique. So we'll start with sketching the graph, which again I think is always a good place to start. So I can tell this function is rational because it's a quotient of two polynomial functions. Basically you have x's in the denominator, so it's rational. So that means it's going to have asymptotes. Now any function like this is going to have an asymptote. The horizontal asymptote would of course be when y is 0, because the degree in the denominator is larger. So you'd have, if x were approaching infinity, you'd have 1 over infinity, which is basically 0. And then the vertical asymptotes happen when the denominator is 0. So that would be when x is positive or negative 1. So I'll go ahead and sketch that real quick. So I have my horizontal asymptote at y equals 0, my vertical asymptote when x equals 2, and, oh whoops, just kidding, when x equals 1 and negative 1. That's my bad. So just ignore those. And then I have I need some points on the graph, so I'm going to set a table of values here. And I'm going to plug in a point to the left of negative 2 or negative 1, and then plug in a point to the right of 1, and then a point in between. So I'll check 0, I'll check 2, and I'll check negative 2. And I'll just plug them into this equation here. So when I plug in 0, I get 1 over negative 1. When I plug in 2, I get 1 over 4 minus 1, which is basically 1/3. And then when I plug in negative 2, I get 1 over 4 minus 1. I still get 1/3. So notice something here. This means the function is even because I plugged in the negative x value and I got back the same y value. So that means it's going to have y-axis symmetry, which will help us when sketching the graph. Okay, so I have this point here, 0, negative 1, 2 and a third, which would be like right there, and then negative 2 and a third, which would be like right there. And then because this value is positive, it's going to be going up to infinity here and then coming down to the horizontal asymptote to 0. This one's positive also, so it'll be going off to infinity there and then approaching the horizontal asymptote of 0. And then this one's negative in between these two asymptotes, so it'll be going down to negative infinity on both sides because it has the y-axis symmetry. So there's our graph. Okay, but now we're going to actually confirm this analytically. Okay, so for step 1, we find the derivative of y. So let's also notice that y is equal to x squared minus 1 to the negative 1. Make it easier to find the derivative that way. So I'll use power rule and chain rule. So the derivative would be negative 1 times x squared minus 1 to the negative 2. Multiply that by the derivative, which is 2x. And then kind of simplify a little bit. So it's basically negative 2x all over x squared minus 1 squared. Okay, then step 2 is you figure out when the derivative is equal to 0. And again, a fraction is only equal to 0 when the numerator equals 0. So you just set the numerator equal to 0. And so we can see that the derivative will be 0 when x is 0. But we also want to find when the derivative is undefined. So then this value, or this function will not exist when x is either positive or negative 1. So these are my critical points. Then in step 3, you plug in your critical points as well as any endpoints, if you have any, into the original function to see if you have any extreme values. Well, this doesn't have any endpoints given to us, and the domain, like x goes to negative infinity and positive infinity, so there's no endpoints with the domain either. So we're just going to basically check the critical points, which are 0, negative 1, and positive 1. So when I plug in 0, which I did earlier, I basically get negative 1, which we can see on the graph too. And then if I go to plug in 1 or negative 1, I end up with 1 over 0, which is undefined. So that really didn't help us figure out if the function has a max or a min at negative 1. So this is where the graph would come in really handy. I can see that this is a local max because the values to the left of it are lower and the values to the right of it are lower. So this is a local max between negative 1 and 1. But if you didn't have the graph handy, what you could do is you could check values of x that are close to 0. For example, you could plug in, say, 1/2 or negative 1/2. So if you plug in 1/2 into the original function, you'd get 1 over 1/4 minus 1, which is 1 over negative 3/4, which is negative 4/3. Since the function's even, you'd basically get the same thing if you plugged in negative 1/2. So what I can see is to the left and the right of 0, the values of y are less than they were at 0. At 0, the y value was equal to negative 1. To the left of 0, the y value was negative 1 1/3, which is less than negative 1. And to the right of 0, it was also negative 1 1/3. So this would also tell us that we have a local max at x equals 0. And the max is equal to negative 1. Okay, last but not least is a piecewise function, and this will help you with numbers 41 to 44 from the textbook. It wants you to find the derivative at each critical point and then determine if you have any local extreme values. So we're going to basically do the same steps. I'm going to start by sketching the graph. So for this one, I can see that when x is less than 0, my graph is going to be linear with a y-intercept at 3. But I'm not including the point at 0. At 0, it would have been 3, so I'll put an open circle there. To the left of 0, basically it had a slope of -1, so the line was going down at the rate of -1. So it was going down 1 over 1, down 1 over 1, down 1 over 1. And it's linear. Then to graph the parabola, I'll just go ahead and plug in some points. I'll plug 0 into the function here. And I'd get 3, so I'll go ahead and fill that in. So I know the function's continuous because these are both equal to 3 when x is 0, so that's helpful. Go ahead and plug in 1, and I get 3 plus 2 minus 1. 5 minus 1 is 4. And then I'll go ahead and plug in 2. Get 3 plus 4 minus 4 would be 3. So it looks like the function's going to go like that because it's a parabola. Okay, so something I noticed right away from sketching the graph is I have a corner right here at x equals 0. So that'll be one of my critical points. And that's because the derivative on the left is not equal to the derivative on the right. Okay, but let's go ahead and begin with the steps. So step 1, I'm going to find the derivative. So on the left-hand side, the derivative is going to be -1. That's for x less than 0. And then on the right-hand side, the derivative would be 2 minus 2x. And that is for x strictly greater than 0, because remember, the derivative does not exist at 0. There's a corner there. Okay, then step 2 is going to be to find when the derivative is either equal to 0 or is undefined. So I know that -1 will never be 0, so I won't worry about that one. I'll just set the right-hand side equal to 0, and I can see that that would be equal to 0 when x is equal to 1, so that's one of my critical points. But then I also have a corner, which we found by graphing, at x equals 0. So these are my two critical points. Then in step 3, I will figure out whether these are max or min values. So I'll plug these back into the original function. Well, I sort of already did that earlier, actually. I did y of 0 and found that that was 3. And then I would plug 1 back in, but I did that earlier also and found that that's 4. So it turns out that I have a local minimum, and again, it's local because, look, the function is going up forever and then down forever. So this is a local min because if you ignored like this part, it's definitely the lowest y value on a small interval of x values, but not the lowest overall because the function goes down forever. And then if I ignored this part, I can see clearly that I have a local max where x is 1 because it's the highest over this interval of x values. But if I were to include the whole thing, it's not the highest overall because the function goes up forever. So I have a local max at x equals 0, and it's equal to, or sorry, local min, excuse me, at x equals 0 and it's equal to 3, and then I have a local max at x equals 1, and the max is equal to 4. All right, so I will see you in class.